Have you ever wondered whether the constants in physics are actually constant? Like, are they the same across the entire universe? For example, the gravitational constant, right? It tells us how strong gravity is. It says if you've got two objects of whatever masses, whatever distance, they'll feel a certain amount of force due to gravity. And the number that relates those two is 6.67430 times 10 to the minus 11 Newton meters squared per kilogram squared. And it's known as capital G or big G. You might recognize this equation as Newton's equation of gravity that we all learned at school. That tells us the strength of gravity at lower speeds like on Earth and in the solar system. But it also appears in Einstein's equations for gravity from general relativity, which, describe how space itself is curved by heavy objects to give the effects of gravity. And this is much more accurate for things around heavier objects and things going at much faster speeds. So in each of these equations, capital G, the strength of gravity, is a constant. You've probably grabbed that number before, plugged it into the equation and worked out the answer at school. But is the strength of gravity truly the same across the entire universe? And if it isn't, and if it is allowed to vary, could it actually help us solve something known as the crisis in cosmology? Now, measuring the strength of gravity here in our backyard of the universe is something that was first done in 1798 by Henry Cavendish. And the number he got was actually only 1% different from the modern value that we quote today. The value hasn't changed much since then. We know the strength of gravity to far less precision than we know any of the other physical constants. And that's because it is notoriously difficult to measure the strength of gravity because it is so much weaker than the other forces, like the strong force binding atoms together, or even magnetism as well, right? So like this is just a normal fridge magnet, right? This is the little magnet on the back of this clip. And magnetism, you can stop and think about how much stronger magnetism is. If you think about, right, if I've got this little hair grip here, this bobby pin, this magnet can hold up that bobby pin against the entirety of the Earth pulling down on it due to gravity. That tiny magnet wins that fight. And if you run the numbers, you'll see why. Magnetism is 100 billion times stronger than gravity. And so now you can probably see why measuring the strength of gravity is so difficult and why we've ended up with such variation in the numbers that we've measured and also the uncertainty on all those measurements over the years as well. And because of that, people started to wonder, well, is the strength of gravity actually constant, or does it vary? There's a couple of different questions you could actually ask here. The first question would be, does the strength of gravity vary with time? Is it getting stronger with time? Is it getting weaker with time? Is it varying with some sort of set pattern, or is it just varying randomly with time? The second question you could ask is, does the strength of gravity vary with position in space? Is the strength of gravity that we measure for here on Earth and in the solar system the same as for the next star system over, or in the next galaxy, or even on the other side of the universe entirely? And then the third question you could ask is, does the strength of gravity vary with the scale of the object? For example, is the strength of gravity the same here on quite small scales, sort of like with the Earth going around the sun, as it is around incredibly dense objects like black holes, or on incredibly large scales when you have an entire galaxy or a galaxy cluster, or even the entire large-scale structure of the universe that we call the cosmic web? They are three very big questions, and you might think that we've not got a hope in hell of being able to answer any of these, but actually we do, thanks to the observations of the universe that we've made and the astrophysics that we can do. Sometimes we can answer them directly, and sometimes we can answer it indirectly. Take the first question, for example. Does the strength of gravity change with time? Now, for this one, we do actually have measurements of the strength of gravity, at least here on Earth, over the past 200 years that we can investigate. Okay, well, how have they changed with time? Problem with that is that 200 years is but a drop in the ocean compared to the universe's age of 13.8 billion years. So any study that you do is going to be incredibly limited and not tell the whole story. That didn't stop Anderson and collaborators though in 2015, who claimed that there was a periodic variation in the values of the strength of gravity measured by the different experiments over time. They even wondered if it had something to do with the solar cycle and the number of sunspots. This caused a huge stir in the physics community when this was released, because periodic variation is not something we could ever explain. But then the work was very quickly debunked, because it turned out that Anderson and collaborators had used the dates that the experiment was published in a research paper rather than the date that the experiment was actually done. When you take that into account, the whole argument breaks down, right? There's absolutely no periodic variation with time at all, and not even any random variation either that can't just be described by the uncertainty on the measurement. So to test this properly, we're going to need measurements of the strength of gravity over, millions, if not billions of years. And you're probably thinking, well, we don't have that data, so what a shame, we're never going to be able to answer this question of whether the strength of gravity varies with time. Except we can do this astrophysically, because light takes time to travel to us as it travels at its speed limit, the speed of light. So what that means is that as we see more distant objects, we're seeing them as they were billions of years ago, and therefore how they behaved under the strength of gravity, whatever it was, billions of years ago. So for example, if we spot a supernova, in a galaxy at a huge distance, billions of light years away, especially when they're the type that always explodes with the exact same brightness due to a white dwarf reaching a certain critical mass because it's stealing matter away from its companion star that it's orbiting around. That critical mass depends on the strength of gravity at that time, and also at that position in space as well, if we're sort of jumping ahead to question 2. This is what Mould and Uddin studied in 2014, whether the strength of gravity changed with time. And they found that the change in capital G was only 0.1 parts per billion per year over the 9 billion years they had data from distant supernova whose light took that long to travel to us. So it seems like the answer to question 1 is no. And it's not just this study that found it either. There's been lots of different studies that have tried to do this either with the moon, the solar system, or with pulsars, or with seismic activity on the sun. I'll link a review paper down in the video description below if you want to check out all of the details of those studies. But despite all that, this idea of the strength of gravity changing with time has reared its head again very recently as a way to explain dark energy. Dark energy is the name that we give to the thing that is causing the expansion of the universe to accelerate, to speed up. We don't know what it is. We don't know what's causing it. But in February 2022, Hanimelli and collaborators again looked at allowing the strength of gravity to vary with time. So instead of some mysterious, unknown, dark energy, whatever that might be, they essentially said instead it would be changed by the fact that you have a different pull of gravity on all of the matter in the universe. And to get at this conclusion, they used, again, the data from supernova, but also data on bigger scales, something called baryonic acoustic oscillations, which is essentially fluctuations in the distribution of matter across these huge cosmic scales. And they ended up making this fit for how the value of the strength of gravity has changed with time compared to the current value, finding a 5% variation over the past 11 billion years, which, although very small, they say is enough to explain the accelerated expansion of the universe. Now, while this is a really nice idea, it hasn't fully been tested yet. It hasn't been tested against data like the cosmic microwave background, which is that echo of radiation left over from when the universe first started expanding. It's a little bit more complicated to test this with cosmic microwave background, but I'm sure they're working on that at the minute. Plus, we also need to work out how this fit in with our current best models of the universe as well, which say that 70% of the universe's energy budget is in dark energy. So while it's an intriguing idea and an exciting preliminary result, it's not quite a fully fleshed out hypothesis yet. So let's just, put a pin in that idea for now, and we'll see what happens over the next couple of years. Let's move on to question 2 now, on whether the strength of gravity changes with position in space. Now, obviously, we do not currently have the technology to up sticks and travel to the next star system over or the next galaxy to measure the strength of gravity there. But that supernova study I showed before technically measured whether the strength of gravity changes with space as well, because they looked at a supernova in that direction and over in that direction and over in that direction, all the different directions, and found that it wasn't exactly very different. But that study is limited because that strength of gravity also depends on our knowledge of what that critical mass is that the supernova goes off with. And so there is some uncertainty there. It was maybe perhaps an indirect measurement rather than a direct measurement. But we can measure this much more directly with stars that are a little bit closer to home. For example, in a binary star system where you've got two stars orbiting each other. My colleague in Oxford, Harry Desmond, and his collaborators actually managed this in 2021, the first direct measurement of the strength of gravity outside of the solar system, using 6 binary stars in the Large Magellanic Cloud, which is a dwarf galaxy orbiting the Milky Way that you can actually see in the southern hemisphere if you're lucky enough to live there and be beneath such incredible skies. But again, there's a lot of uncertainties here with this study too, but they found a value of the strength of gravity at 93% of what we find in the solar system, but with a rather large uncertainty on that measurement as well. This study though was limited as well, right? 6 binary stars, that's it, that's all they looked at. That's not enough to give you the, the accuracy and the precision that you actually want for a measurement like this to then be able to shout from the rooftops that, you found an actually different value to what you get in the solar system. But this was the very first study of its kind. It was the very first direct measurement of the strength of gravity outside of the solar system, even beyond the Milky Way as well, right? Because it was in the Large Magellanic Cloud, which was an achievement in itself. And, very first study of its kind, just having maybe some tantalizing hints that could be something going on, but we just don't know. But I'll get Harry to keep me in the loop in case him and his collaborators have anything new to report in the future. And finally, question 3. Does the strength of gravity vary with scale? This one is a little bit more difficult to answer. But let's start with the smaller scales around very dense objects like black holes. We have tested the predictions of general relativity in so many different places when it comes to black holes. From black holes in orbit around stars, to the stars orbiting around the supermassive black hole in the center of the Milky Way, to the gravitational waves from black hole mergers, to the supermassive black hole in the galaxy Messier 87. The predictions that general relativity makes for the constant strength of gravity have time and time and time again matched the observations that we make on those scales. But on larger scales, like in galaxies of billions of stars or galaxy cluster scales, the predictions that general relativity with a constant strength of gravity make don't match the observations. And it's this with a lot of other things that give rise to the idea of dark matter, this matter that doesn't interact with the force of electromagnetism, i.e. light, but does interact with the force of gravity so that we can tell that it's there. Kind of like how, you see the trees move, but you can't see wind. We actually need far more dark matter to be there than there is normal matter for the predictions of general relativity to make sense. It's not just that though. We've got lots of other evidence for dark matter. You can check out the video I've made on that before that summarizes the history of our understanding and all the evidence that we've collected, from the rotation curves of galaxies to galaxy clusters and lensing to the cosmic microwave background to how structure even forms in simulations of the universe to the bullet cluster as well. Explaining one of those things that I just listed individually without dark matter is possible with something called a modified theory of gravity. Again, I've talked about the different theories of gravity we have instead of general relativity in another video if you want to check that out. But no hypothesis has been able to explain all of those observations together without some form of dark matter in the universe that doesn't interact with light. The best we currently have is still general relativity plus about 25% of the universe being made of dark matter. But even that has some issues and some conflicts, and you will not find one astrophysicist that would ever claim that that theory is perfect. Because when we model the entire universe, what it contains and the forces governing it, we fit what we call a cosmological model with general relativity governing it in terms of gravity. And we try and get a measurement of, okay, what is the rate of expansion of the universe? We actually get a different answer if we use data from nearby objects like supernovae and those on much larger scales, like the baryonic acoustic oscillations I mentioned before or the cosmic microwave background. So in trying to explain why these could be different, one thing people have suggested is if the strength of gravity was allowed to vary with scale and space and time. And one of the most popular ways of actually doing this and incorporating it into our big cosmological model is known as Jordan-Brans-Dicke theory, where instead of a constant value of g, the strength of gravity, you instead have what's known as a scalar field to describe the strength of gravity. What that essentially means is that, at every single point in space and time, you have a different value for the strength of gravity. And not only that, matter and light could also experience different strengths of gravity as well. You'll see studies doing research on G matter, the strength of gravity clumping material together to form objects like planets and big structures like galaxies. And then also G light, the strength of gravity deflecting light due to the curvature of space. If these two things are equal, it's called no-slip gravity. But in most of these theories that modify general relativity in this way, they're not equal, which adds a whole other layer of complexity to this. These tweaked general relativity theories are tested using big cosmological surveys that take images of every single part of the sky to record what we find there, and then essentially map out the distribution of matter and where light has been deflected into these big arcs. I've covered one of these big surveys before with the public data release from the Dark Energy Survey last year in 2021. Then when you've got this survey data, you can take that map of all the matter and where the light is bent, and you can fit your big cosmological model that allows the strength of gravity to vary. And you actually find it gives a really good fit to the observations that you have because, well, it's basically just general relativity, because they find that the strength of gravity doesn't really change much and doesn't change on these cosmological, very large scales. People quote the ratio with the current value. So in this paper by Simpson and collaborators, they're quoting the difference ratio. So closer to 0 is closer to that constant value that we quote. And they get a 5% difference, but with a 25% uncertainty on G matter and a minus 5% difference with a 30% uncertainty on G light. Or in this paper by Uddin and collaborators, where they actually quote the ratio, so closer to 1 this time is closer to that constant value, and they find that G matter is 99.7% of that current value that we measure here on Earth, with a 2.9% uncertainty. Essentially, both of these studies, and many other studies that have looked at this as well, find that within our uncertainties on the measurement, the strength of gravity doesn't really change much. And what's more, it doesn't even help resolve the problem of that disagreement between the expansion rate of the universe measured with different scales of data. Which was the whole reason, right? It was the main motivation for why these studies investigate this idea of varying the strength of gravity in the first place, which is quite disappointing. But again, these studies are still limited by the data that they have. In this case, they're limited by how faint of objects they can see and how small the thing is that they can resolve as well in terms of making that map of where all the matter is. They had a bigger telescope that would look at each area of the sky for much longer, then they get a much more detailed and precise map of where all the matter was in the universe and where the bending of light was as well. Like, for example, with the European Space Agency's Euclid telescope, which will provide much higher resolution data to test these models with a higher precision, which will give us less uncertainty on our measurements, whether that's the measurement of the expansion rate of the universe, or whether it's, measurement of the strength of gravity changing with time or space or scale. Whatever it is, hopefully what this data will do is either completely break our best current cosmological model we have of the universe, which means we have to, scrap it up and start again, and we learn so much more new science. That would be amazing. Or it will make just one measurement that, maybe looked a little bit anomalous this entire time, that much more precise, so that everything just falls into place. And it turns out there's no conflicts at all. It was just our measurement, or there was biases somewhere. The good news is we don't have long to wait, with the Euclid mission set to launch in 2023. So that finally we can solve the, crisis in cosmology where all these measurements don't agree, but also understand whether the gravitational constant truly is a constant. I just had to go on a hunt for a magnet, which I knew we had, and something like a paperclip or a safety pin or, anything that would stick to the magnet. Apparently we don't have any of that in our house? No. What we do have is a bobby pin or a hair grip. I mean, I have 100 of them. And it was the only thing that would stick to the magnet. So to test this properly, to say this properly, you need to chill out. Because dark energy is Because dark energy is the name of the thing, Dark energy is the name of the thing that we give to, Dark energy is the name that we give to the thing that causes the accelerated expansion of the universe. Oh, we got there in the end. Oh, gravity's not the same as it was. Oh, gravity's not the same as it was.